Thanks very much. So thanks for the opportunity to speak today on this work we've been conducting on RPAS radiometrics. We've assembled quite a project team, and we're coming at this question from two different angles. So myself, Easton Aaliyah, and Brent Ward are quaternary geologists, and so we're coming at this from a sedimentology perspective. Rob Shives, Mel Best, Steve Monkhouse, and Nicholas, who we've just heard from, are coming at this from geophysics and a physics perspective. And they bring a wealth of knowledge to this project, and really that wealth of knowledge is really required to try and answer this question. And so we are quite lucky to have them working with us. Okay. So dispersal and tills. Let's talk about tills firstly. Tills are a glacial sediment. They're sediments that are eroded, transported, and deposited by a glacier. The tills that we specifically sample are a facies of till called a subglacial till. And so all that erosion, transport, and deposition is happening in the subglacial environment. And the reason we target that facies specifically is that those tills have a predictable transport history. So if we understand ice flow direction, we understand transport direction, which is really important. Short transport distances typically happen with those facies of tills. And at the end of the day, they represent a large exploration target. And you can see that in the top panel here in this slide, where the subcrop source is quite a bit smaller than the dispersal train that's expressed at surface. On the right side of this slide, you'll see a textbook example of a subglacial till. And then Aaron in the top there sampling a subglacial till. And I'll give you a tip right now. If you're ever out sampling, if you are sampling with a shovel, you're probably not collecting the right material. And you'll see Aaron up there with a pick and collecting what is a really over-consolidated sediment. That's how we would describe a subglacial till. So dispersal trains in tills are just defined by contrast. And that contrast can be anything from an element to a mineral to even a boulder for that matter. And that's what's shown here in the top part of the slide. When we're out sampling, whether we're collecting these physical samples or flying a radiometric survey, this is actually what we're trying to define. And that dispersal is characterized at the head by a very sharp drop or abrupt decrease in contrast, in values, representing extreme contrast back to background. In the down ice direction, those values decrease exponentially more or less. So it's a more gradual decrease in the down ice direction. And that's how these dispersal trains are defined. So for decades, we've been defining those dispersal trains based on geochemistry and elemental concentrations. For about the last 10 years or so, the focus has really changed, and we've been working on mineral assemblages and mineral separations, or an indicator mineral method to define that dispersal. And shown here is a suite of indicator minerals that we've recovered from till samples in British Columbia from around 4 different porphyry deposits. And so the question that really defines our project and underlies everything that we're doing and we're going to present today is, can airborne, and I've added surface just to emphasize the fact, geochemistry define dispersal? And Rob Shives has been saying for decades, yes, yes, yes. And he has all kinds of fixed wing data that can support that, which I'll show you here in a minute. The question for us is, can an instrument with a much smaller crystal flying in an RPAS platform sort of replicate those data? That's kind of the goal of the project. So quickly about porphyries. Porphyry systems or porphyry deposits, they're a really important exploration target in British Columbia, and a lot of money is spent every year trying to find the next porphyry mine. Recent work on these systems indicates actually that the sort of end members, alkalic and calc-alkaline, they actually have a lot more in common than was previously thought, including all these alteration zones that you see here. They'll be present in some form or another. The devil is in the details, so how they show up, I think, is probably a difference. But the fact is, most of these alteration zones do occur, even a lithocap over an alkalic system. That does occur. So one of the most important alteration zones really is this potassic alteration zone right in the center of this deposit, because it is intimately associated with mineralization. And of course, because it it's potassically altered. There's more potassium there, and you're going to hear that throughout this talk. Potassium. When we think about the end members, alkalic and calc-alkaline, one of the big differences, obviously, is the host rocks for those deposits. Alkalic deposits are typically hosted in these cyanites or some version of a monzonite. These are average potassium values for those rocks, just to give you an idea of what they start out with in terms of potassium. Calc-alkaline, on the other side of the QAP ternary diagram, they are most often hosted in something like a granodiorite or even a tonalite. So even going farther to the calcium side. And then any potassic alteration would be in addition to that. And so the factor, I think, depends, the answer you get depends on who you ask. It can be anything from a factor of maybe 1.25 to maybe even 2. So you might be able to double the potassium concentrations in some of these rocks by potassically altering them. So Ron did a great job this morning talking about advantages and disadvantages, why you might consider using an RPAS for whatever you're trying to do. Most of these he's already covered off. I've used here in the last point, which is actually what gets me most excited about this method, is that these data can guide exploration programs. I'm saying in near real time in reference to the fact that you can fly a survey one day, process those data that night, and then use those data to guide the exploration program the next day. And if you talk to a geochemist right now, I think wait times for commercial labs are somewhere on the order of 4 months. So when you collect a sample, you submit it. In fact, we did this. We submitted our samples in October as part of this project. We didn't get data until it was February. So that's pretty tough. That's pretty tough when you're trying to run an exploration program and move the project along. So this last point is probably what gets me most excited. Ron was speaking about the data happening. I would call it almost in real time, which is even more exciting. And so fingers crossed we get to that point. So here's the gear we lugged around with us last summer. It's about a truckload worth. Each of those boxes is a system in itself. And so I'm really glad to hear people using RPAS, because it's really about systems as far as I'm concerned. So our goal last summer was to get each of these systems to work with one another to collect geologically meaningful data. And so the talk today is really just going to focus on 2 of these boxes and the instruments contained within them, or the equipment hardware. Oh, sorry, I had to hit the laser. The first one is, I'm hitting the wrong, doesn't matter. Oh, there we go, yeah. So the first box is this box here. That's what contains our M600, the platform we use for this work. The other one is this box here, which contains RSI's gamma ray spectrometer. Yeah, it was, Mini 2. So the M600 really was the workhorse last summer. It's an exchangeable payload RPAS, can carry up to 6 kilogram payload. Flight times vary from 20 to 40 minutes, all dependent on the payload that you're carrying. And what we recognized very early on in the project, and people have already spoke about this, is the need to fly low and slow with confidence. So basically at the end of the day, the measured values we're collecting are a reflection of geology and not a change in sensor height above ground. So to that end, we installed a radar altimeter. It's the one that Ron spoke about earlier. That in combination with flight planning software, talking to a flight controller, enables us to maintain a constant altitude above ground. And that's a preset constant as well. And we'll talk about that in a minute. So here's a photo of the RS-350. We mounted, I'm getting ahead of myself a little bit, but we mounted 3 different instruments on this M600 in the summertime, last summer, sorry. And by far, this was the easiest instrument to mount and integrate with that platform. RSI has done a really great job. So I won't go over the details. Fortunately, Nicholas did that for us already. It came from the expert. This is just a video of the M600 carrying that spectrometer in a typical clear cut in central British Columbia. It's actually flying at 5 meters above ground level. And I think right when it turns the corner here, you can see the wash in the brush in that cut block. So there you go. And we fly with the landing gear up, of course. So in terms of flight line spacing, the surveys we flew varied from 7.5 to 10 meters. In terms of elevation above ground or altitude above ground level, we flew as close to ground as we could, and we basically had these three sort of values that we typically stuck to: 5, 7.5, and 10 meters above ground at 2 meters per second. So we also flew magnetometer surveys. I'm not going to talk about that here. I just wanted to show you this video because it's another, it's probably a better example of what these cut blocks look like, and they can be pretty nasty. So this video is being recorded at a constant altitude above sea level. So anytime you see that M600 going up and down relative to the sort of plane of the camera that's doing the recording, that's the altimeter instructing the M600 to change altitude so it can maintain that constant altitude. So our surveys, because we needed to fly low and slow, our surveys really were limited to cut blocks in central BC. So at the end of the day, about a month's worth of field work, we flew 155 blind kilometers of gridded terrain following autopilot surveys. And those were incident-free line kilometers, I'm very happy to say. And my bosses were happy about that as well. I think we can all appreciate once that aircraft is up in the air, there's a lot of money in the air. And so we fortunately did not have to fix or replace any instruments. So as I mentioned, over each of these survey areas, we flew magnetics, radiometrics, LiDAR, and air photos. We won't talk about those today. It's really just focused on radiometrics. But Easton and myself would be happy to talk to you about any of these other data sets that we collected at lunch or tomorrow. So to supplement an existing data set, which is quite incredible, of till geochemistry and lithogeochemistry, we did collect a couple of other samples this past summer right within the survey areas that we were working in. And really, method development challenge or conundrum for us was trying to find a flyable cut block with favorable geology. And that proved to be quite a challenge. Okay, so on to regional radiometrics. This is a compilation of surveys collected by the GSC. And so we're now, this is actually plotted at a very similar scale to that previous locations photo I just showed you, but just a wider extent. And so you may be looking at this, I hope you are, and thinking, wow, that looks a lot like that first slide that Travis showed us on dispersal. And it really does. There's a high, sorry, I should mention this is potassium. There is a bunch of high values here in these gridded data. They drop off very quickly in the down ice direction. Ice flow here is to the northwest. They drop off very quickly to background in the down ice direction, and they sort of gradually decrease in the up ice direction. And so we're actually looking at dispersal at a district scale, really, of potassium. A couple of other pieces of information. If you were to overlay a superficial geology map into that magenta or pink circle, you would see that it's dominated by tills. Something like 80 to 90% of that is covered by tills with very little outcrop, and what's there, it's very isolated and discontinuous. So that really is, it's a surface geochemistry map of the top 30 centimeters, and that top 30 centimeters is subglacial till. And so the next slide here, we're going to get more into the geology, but it's these potassium-rich rocks at Mount Poly Mine and associated with that deposit there that are causing this high K radiometric signature. And so, of course, the ultimate question is, can we go into one of these areas in more detail and actually measure that same dispersal with an RPAS instrument? Okay, so geology really quickly. It really comes down to potassium or no potassium. There's a panel here of Ashcroft's formation sediments sandwiched between nuclear group, mafic volcanics, and volcaniclastic. So really, those are in the big picture, low potassium rocks. What got us really excited about working here are the rocks at Mount Poly Mine. There's a photograph of outcrop at boundary zone, which is a potassically altered monzonite. And it's actually called a crackle breccia, and that the breccia class itself were actually cemented with magnetite, which of course makes it an ideal spot to go fly a magnetometer survey as well. And so our survey areas are overlaying on top of this image. The two survey area 7 and 8, those are both over subglacial tills. And we sampled tills there, we described tills there, so we're confident those were subglacial tills. Survey number 5, the area wasn't big enough to fly a gridded survey. And so what Easton and Brent did was actually hover the instrument at different elevations above this outcrop and collected data over that, which I'll show you here in a second. Okay, so the next couple slides leading up to presenting our data have existing data that we can compare back to, and that was one of the reasons we came to this this specific study area, is that there was so much existing data that we could compare back to and actually compare, contrast how this instrument was operating or functioning or detecting compared to more traditional fixed wing instrument. So the radiometrics data you are going to see as sort of a background to these slides was another survey flown by Rob Shives when he was at GSC. What struck me when I started putting this table together was the instrument size and the instrument volume is just significant. And then of course the weight. So this is like a 50-liter instrument basically that weighs over 800 pounds. And we were trying to do the same thing with an instrument that is a third of a liter and weighs just over 6 pounds. And there's other survey parameters here that are worth noting, in particular velocities. There's quite a bit of difference in velocity, and of course terrain clearance. So the fixed wing survey was flown at 125 meters above surface, and we were flying 7.5 to 10 meters above surface. Really quickly, the geochemical data I'm going to show you, they belong to two compiled databases that we have produced at the BCGS, the other BCGS. The important thing to note is these are total determinations. So they are characterizing all potassium in those samples, regardless of the mineral that potassium is being held within. So we would consider those total determinations. Okay, so onto the data. Again, in the background here, this is the regional radiometrics. This is 100-meter cell size data. Our survey areas are thrown on top. Ice flow direction here is given towards the northwest, all very important. What I've also overlaid on here are polygons from superficial geology maps that exist for the area. The gray ones, gray polygons are an organic unit. So these units are rich in organics, typically greater than 1 meter thick, and they really are masking the lithic soil horizons below, both because of just thickness, so that lithic horizon is now greater than 30 centimeters below surface, but also because of water content. These sediments can hold a lot of water. Also on here, magenta colored polygons. Those polygons are till veneer units, so they are thin tills which actually often have discontinuous bedrock outcrop exposed in them. So these are areas where you'd expect higher surface geochemistry values to show up. The organic units are where you'd expect lower geochemical surface values to show up, and it holds true quite well when you look at the distribution of those polygons. Overlaying here now are 2 more data sets. The till geochemical data set is shown with black dots. Those black dots are labeled with potassium concentration. That's elemental potassium given in percent. The white dots are the lithogeochemistry data set with potassium concentration shown or labeled next to the point. So this really is a surface geochemical map. These are till samples that we collected at surface or bedrock that's exposed at surface. And so the radiometrics should follow that quite closely. And I think you see in the regional data that they do. I've made 2 circles here. We've collected a sample in each of the survey areas that we worked in. Again, that's potassium percent, ranges from 1.85 to 2 at survey 7, and 1.8 to just about 1.9 in survey 8. Keep those locked in your head, because the last slide I'm going to show you our data superimposed on top of those points. So here are data we collected at survey 5. Again, remember this was basically hover testing or acquiring data well in hover. There are the 3 elements are shown here, potassium on the right, going to higher energy towards thorium on the right, on the right, potassium is on the left. Each of these clusters shown here in these graphs are essentially 2-minute or 120-second time windows. X-axis is time, Y-axis is concentration. And so you can see in these graphs that, at least with potassium, there is attenuation as the aircraft or sensor distance between ground is increased. And we'll come back to why that's important in a moment. In the case of thorium, it's actually pretty hard to tell. There may be really not much of a difference, especially statistically, I would say. Uranium is kind of funny in that there's more attenuation at 5 meters and 10 meters, which is not what you would expect. And so basically this relationship between attenuation resulting from an increase in sensor distance, I think it kind of falls apart in the statistical noise. Just a summary table really quickly to show you what that detector was seeing when it was doing this work. So in the case of survey 5, when it was sitting on the ground, it collected about just shy of 50,000 counts over, that's summed over the 120-second period. Gives total counts for that, counts for potassium, potassium percent, and then height corrected. So obviously this was collected at 0, so there is no height correction. But the rest of these surveys were collected, or data were collected at some elevation above surface. And we applied a correction factor to essentially bring them, for them to represent what the chemistry is at surface, taking into account that attenuation curve. Okay, so here are our data. This is survey 7, survey 8, and then survey 5. There's dimensions here to give you an idea for scale. So these were actually fairly small surveys. Some description here about what was applied or how the data were processed. Nicholas talked about NASVD, which was great, height correction. These data were gridded using an inverse distance weighting. And what's important to note is these legends are actually different. So same color ramp, but the values represented are actually different. And the range of values is actually not that great. It's from just over 2% to just over 2.2% in those plots. So here's the data at survey 5 shown a little bit differently. Concentration is on the x-axis, y-axis is elevation above surface. So this first data point was when the instrument was on the ground and it was collecting data. This is sort of a best fit curve that shows how that attenuation actually takes place as sensor height is increased. And we use that curve to height correct these data. Just for interest's sake, this survey was collected at 7.5 meters above surface. These data were collected at 10 meters above surface. So I should have mentioned, there's quite a bit of variability there, not in terms of the values, visually there is. I don't think we know yet exactly how to explain all of it, but I can say with confidence that there's a lot of local, very local site variability. And so, and I think that explains at least some of it. So here's a sample site. This is at survey 8. Where the top 30 centimeters is dominated by a lithic soil. So it's mostly a B horizon or a transition from a C to a B horizon. So it has a strong gamma ray signal, if you want to think of it that way. This was a sample site in survey 8, the one closest to Mount Poly Mine. And you can see quite a difference in what that top 30 centimeters looks like. This is actually dominated by forest litter. We'd call it an LFH horizon, or maybe even an AH, which is more of a decomposed version of that. In other words, the lithic soil is deeper, and these water-rich sediments are probably attenuating those signals. Okay, and so the last slide, this is the regional picture with 100-meter cell size data in the background. The whole rock, we call it whole rock geochemistry. Total potassium values in percent for till samples and for bedrock samples. And then our data are now ramped or colored using the same ramp as the regional data. And I think I told you that the till sample we collected here was about 1.8% potassium, something like that. And this one here was actually the other way. It was a little bit higher. It was getting closer to 2%. And so if you take, actually don't have an average value here, but we've provided a max and min, and you can see that when you look at the data as a whole, they actually fit, I think, fairly reasonably well within the regional data, but also the total determinations that we have for the till samples right within those survey areas. Okay, so just to summarize, can RPAS radiometrics detect glacial dispersal? It's a yes, and that's pretty great. And we demonstrated not on the magnetic side, but high quality data, magnetics and radiometric can be acquired using RPAS platform. As shown those last couple slides, the RPAS data compare very well with existing data, and that was kind of all of the sort of the point of the proof of concept or testing the method. How does it compare? The biggest challenge really for us was finding areas to fly with favorable geology, and that is tough. But I think we've all worked in different parts of Canada and parts of the world for that matter, and I think when you start thinking about what's required of the instrument to collect high quality data and what flying conditions might be ideal for that, media, for me, I've worked in the Arctic a bit, and so anything above tree line, I think this would be an amazing method, whether it be alpine or Arctic, and then over a stronger potassium, uranium, or thorium target. So we're measuring very low concentrations in the big picture of potassium and subtle changes in potassium. And so anyways, I think that those would be more ideal survey conditions. Just really quickly, we're going to be out again this summer doing some more of this work. So we'll have more data to present next year at this time. Really quickly, this project was 3 years in the making. We had all kinds of help from all kinds of people, and I just want to acknowledge them here, and especially Ron Bell. He was extremely generous with his time and his experience and knowledge, and so we really appreciate it. Thank you.
Thank you, Travis. I'm a little embarrassed. I generally help people without ever thinking about getting any sort of recognition, but thank you for the recognition. Or even pay.
Yeah, it was free. There was no pay.
Yeah. I think you did a remarkable presentation in showing how the geoscience, the geology, the geophysics is all interconnected, and it really leads to a real positive objective, a positive result. I'm just excited about geochemical mapping with geophysical methods. I think you've given me a lot of encouragement about continuing down the path of using drones to map geology. And I don't know if I shared with you this before, but I am the one and only living geodronologist on the planet Earth. So I shared that with Travis a while ago. He found it funny.
I want to know how to become one, but you never gave me an answer.
Well, I've got inspired. I'm going to do a certification program.
Oh, perfect. Okay.
So
good.
We can do it online, and you don't have to travel to the US, but if you want to, it's okay. So does anybody have any questions for
Absolutely.
Yeah, you saw one that was a kind of cross section of the till and sort of really very beginning.
Yeah, we're almost there. Sorry, I should have canceled out of it and went. Maybe I should still do that because I don't want to burn up your time. This one here, is that the one?
Yeah, this one.
Yeah.
So I'm not experienced in geology and glaciology.
Yeah.
But it seemed like you were saying from the surface distribution, you were able to infer the direction of the glaciation. And so you can kind of say, all right, I think this came from this way. And the question is then, okay, how far? And so I'm wondering, based on that surface pattern, are you able to infer that pitch angle, or is it consistent amongst all glaciers? And so how do you kind of go how far along that distance? How do you infer that? Or do you just geophysics it all?
No, so that is the $1 million question. And I get asked that all the time. How far, if you end up with an anomaly of some sort, again, all defined by contrast. Contrast can be any element you like. It can be gold grains, whatever. Once you identify that, how far up ice do you have to go to hit that target? The subcropping bedrock source. There are all kinds of examples of exploration programs that have focused on that head and have drilled a hole and ended up in barren outcrop. And so that is the $1 million question. I can give you some ballpark numbers. In BC, this offset is sort of on the order of 1 kilometer or so, or can be. But there's a lot of variability, and that variability is dictated by the thickness of the till unit itself. So a really thin till unit, transport distance can be on the order of tens of meters, maybe 100 meters. As tills get thicker, this transport distance increases. And so that's another question I get asked all the time. How deep is bedrock? That comes from geochemists, geophysicists. It's extremely hard to say. Bedrock topography is variable, almost exactly as depicted here. And so that's a really hard one to nail as well. Yeah, so I was going to give you some more information on 2 more of your points. So one is this dip angle, if you want to consider it that. There's a whole lot of exaggeration here. It's 11 times. So we do that just to illustrate the point. If you take that 11 times out, it's actually very, very flat. That dip of the dispersal train can be detected in trenches by doing vertical profiles. And it varies. I don't think I couldn't even give you a number of what that would be. The last point, ice flow, super important. So I missed this and I should have described it better. We have a lot of other data that we use to figure out ice flow direction. One of the big data sets we use, it's just called an ice flow indicator data set. And so these are features that we observe in bedrock outcrop. They're also features that we observe in landforms that are created by a moving glacier. And so we know with confidence, based on the orientation of those features, which way glaciers were flowing. So I didn't give you that information. We wouldn't really use dispersal to figure out ice flow direction because it's not as easy to do, and we don't have as much confidence in it as we do with these other data sets. And so I think a lot of people here would have heard of a striation, for example. They're just very small outcrop scale features. Those give us a pretty good idea of direction of ice flow. Other landform scale features like crag and tail ridges or drumlins would do the same.
Thanks.
You bet.
Any other, there's another question.
Thanks. Probably a simple one. I don't recall what your line spacing was, but for like the 100 meter by 100 meter cut block, what sort of time was invested in just the radiometric acquisition?
Just collecting the data, yeah. So line spacing for that survey was 10 meters. Data were being acquired at 10 meters above ground level. And that survey was done on a single set of batteries. So it would have been less than, like a half hour at the most, I would say. I don't know if I mentioned, but all the data were collected at 2 meters per second. So that's kind of like a fast walking pace. It's like 7 kilometers an hour, just to give you an idea of velocity. No, with the gamma ray spectrometer, we definitely could have flown fast, but it would be at the risk of reducing counts, or I think counts would have. Oh, there we go. We could have, but we didn't, and we didn't experiment with it. And to be honest with you, it's something we'll probably do this summer, is experiment with velocity. Yeah.
Any other questions? Thanks again, Travis.
Thanks, Ron.